Okay, we'll officially analyze or start analyzing graphs of functions in this section. We kind of had a little preview of a couple of the skills that we want to address within it, specifically vertical line test, and also some sort of sense as how we would use a graph of a function to find the function's domain and range. Now, of course, if a function is presented differently, say as an equation, we have ways of figuring out the domain as we just reviewed. But if your function's an equation, it's a little more difficult to identify the range just based on the equation. So oftentimes what we do to find the range of a function when it's given as an equation is we graph it, any which way we want, graphing calculator, table of values, or what have you. And it's with the graph that opens up the easiest avenue in which to find the function's range. And then, as I mentioned at the start of class, we will interpret function notation and how certain function notations ask us to do different things with graphs of functions. So let's start with a quick recap of how to find out if the graph you're presented with is the graph of a function. And we use something I mentioned in section 1, the vertical line test. And remember, with the vertical line test, we draw any amount of vertical lines through the graph as we want. And if you get a sense that no matter where you draw a vertical line, it's going to cross your graph in one and only one spot, that would mean it's a graph of a function. As soon as any one of your vertical lines crosses the graph in two or more spots, you do not have a function. And that's because with a line crossing in two spots, there's going to be an input getting two different outputs. Long story short, what you want to be on the lookout for is any spot on the graph where a vertical line would cross it in two or more spots. Now, that said, let's look at first of these three graphs. We draw a vertical line right here. It appears that that vertical line crosses the graph in just one spot. I'll include a couple more. How many times did that vertical line cross the graph? One time. What do you think? If I were to draw any vertical line through this graph, how many times would that vertical line intersect the graph? Or let me ask it this way. Are there going to be any vertical lines that cross the graph in two or more spots? Okay, so any vertical line is probably just going to cross this graph in one spot. Can you kind of visualize that, Melissa? All right, cool. So you get a sense that this graph would pass the vertical line test because it's not going to be possible to draw a vertical line going through two or more spots in it. Long story short, this would be the graph of a function. Let me have you try it. Go ahead and see if you can determine if the second graph is a function, and also see if you can determine whether or not the third graph is a function. I'll check in with you in about a minute. All right, what'd you get for the second graph? Perfect. Yep. Look at our second graph. Virtually anywhere you draw a vertical line, it's just going to cross the graph in one and only one spot. Now, you don't have to worry about drawing vertical lines over in this area of the plane. Okay, it really only applies when a section of the graph actually exists. So kind of ignore those cases. But anyway, yeah, there's not going to be any vertical line that crosses this graph in two or more spots. So this will definitely be a function. Whereas with the last graph, it seems as though any vertical line that you draw through it is going to cross it in two spots. There are some cases where the line will cross in only one spot. For example, at these endpoints here, we would have tangent lines. But regardless, with the line that I have on the screen currently, that's one line that crosses the graph in two spots. So immediately it makes it fail the vertical line test. So in this case, not a function. So that's really as easy as it is for determining if the graph is the graph of a function. If you're able to establish that your graph is a function, you might want to use the graph to figure out the function's domain and range, which is what we're going to practice right now. So keep in mind that a graph is nothing more than a bunch of ordered pairs that have been plotted and connected. So a graph is made up of all the possible points, x comma y, that would generate it. So every point has an x value as well as a y value. So when we're trying to find the domain and range of a function based on a graph, we're trying to figure out what are all the x values being used to generate these points, and then what are their corresponding y values. When we collect all the x values that are part of the ordered pairs, we get the function's domain. And when we figure out all the y values that are being used, we get the function's range. Now, geometrically, the domain is kind of like a horizontal measurement of the graph. I'm going to draw it symbolically this way. When we're trying to find the domain, we want to think horizontally. Okay, we want to see, okay, where's the point that's furthest to the left on the graph, and then where's the point that's furthest to the right. So we want to think horizontally when trying to find domain, whereas with range, we want to think vertically. Okay, so hopefully that makes sense, because domain consists of x values, and it's the x-axis that's the horizontal axis. And so we're going to get our domain from the x-axis. As for the range, we'll get it from our y-axis. Now, we have three graphs here. Let's look at graph 1. The instructions say we want to determine whether the graph is that of a function. Okay, and I believe we just established this above. So let's just take care of that real quick. This is definitely a function. It would pass the vertical line test as we saw earlier. So let's start things out from here by finding the domain. Again, think horizontally. Let me ask you this, okay? So what is the first x value that's used on this graph? In other words, what's the smallest x value being used to create this graph? Negative pi. Yep. The graph definitely has a starting point, and it would be right here. Negative pi would be the first value of x being used on this graph. So let's write negative pi. What's the last value of x being used for this graph? Yep, positive pi. Everything in between these two values is being used as well. Otherwise, you wouldn't see the graph, nice and connected like that. Since negative pi is part of a legit point on the graph, I'm going to bracket it on the x-axis, and I'm going to bracket pi as well, and I'm going to shade all the x values that go between these two. And this gives you a visual of the domain. Okay, it's all these x values that are being used to create this graph. And in interval notation, bracket negative pi, comma positive pi. Let's think about the range. For the range, we want to think about what the smallest y value is. And you can actually see where that might be in quadrant 3. This is the lowest point on the graph, meaning that the y value for this point is the smallest y value being used. And all things considered, let's call that -1. The largest y value is going to come from this point. The graph doesn't get any higher than this. And again, all things considered, let's call that +1. And since these are points that are actually on the graph, I'm going to bracket both these y values and shade between them, indicating that every y value between -1 and +1 is being used on this graph. In other words, that's our range. Does that make sense? All right. Let's knock out a couple more, then we'll take our break. Do you guys think that the graph in part 2 is a function? Would it pass the vertical line test? Yep, certainly would. It is a function. And I know kind of the white elephant in the room here is that open circle. We would consider something like this a hole in the graph, meaning that the point doesn't exist. Let's say DNE does not exist. So any point starting at the origin and going along this graph leads up to 4, 3, but doesn't actually contain the point 4, 3. So that's kind of a clue as to how we'll determine between brackets and parentheses when it comes to the domain and range. Let's start with domain. Can anybody offer the smallest value of x being used? 0. Now you'll notice that the point associated with 0 is filled in. So that means x equals 0 is being used. And actually everything from x equals 0 up to 4 is being used. Otherwise there wouldn't be this graph there above this part of the x-axis. But we're not going to include 4 because 4 is associated with this hole. And remember, a hole implies that a point is actually not really there. Okay, so 4, 3 is not a point on the graph. But all the x values that lead up to x equals 4 are being used. So what that means for us, the consequence of that all, is that we'd have to use a parenthesis on 4. And we'll use a bracket on x. And so our domain would be bracket 0, 4, and then parenthesis on the 4. Go ahead and see if you can identify the range. We get in bracket 0, 3, parenthesis on the 3. Woohoo! So yeah, 0 is the smallest y value, and it's actually part of a point that is on the graph. So I'll bracket the y value of 0. And then all y values leading up to 3 are being used. But note that 3 is part of that circle. So y equals 3 is technically not used on the graph, but everything leading up to it is. So that's the reason for the parenthesis on the 3. Now I'm going to have you work on one from scratch with number 3. Just want to make a little tweak to it. It's hard to tell, but there is an arrowhead right here indicating that this graph would continue on, in this fashion. So that's kind of a clue as to how you'll form, your domain and range. That's an important part of both of those. All right, so I'm going to give you a minute or so to see if you can identify if this is a function as well as its domain and range if it is. All right, here comes the big reveal. It certainly passes the vertical line test, so it is a function. The smallest value of x being used comes from this point. It's 2. I'll put a tick mark on the x-axis. That's not an open circle, so that means this point's included, implying 2 is a legitimate x value in the domain, and it goes all the way down to infinity. That's the only way that we could get this graph to continue in this way is if we continue using more and more x values. So bracket 2 comma infinity. Likewise, the range is based on the order pair 2 comma 5. This time we'll use the y coordinate of 5. That appears to be the smallest one on the graph. And then all values of y increase from there on out. And that's kind of the reason why this graph is going up in elevation as it goes from left to right. We'll bracket the 5, and I'll just shade this part like so. And we're looking at bracket 5 comma infinity. Confirmation on this answer. You guys getting the same thing? All right, you guys are rock stars. Let's go ahead and take a 5-minute break. When we come back, we will do some interpretation of function notation using a graph. All right, so I'll see you then. Alrighty, folks, welcome back. Let's get ready to polish off the section of notes. All right. So in our next example, as I was mentioning right before the break, we're going to be looking at a variety of function notations. And what I mean by that is we're going to either plug different numbers into the function notation, incorporate inequalities, or set the function notation to a particular value, and see what sections of the graph, this one here, are pertinent to that particular type of function notation. One thing that I want to do on this graph before we get started is indicate that the y-axis can also be labeled as the f of x axis. In other words, any y value on this graph is f of some particular x value. And that's definitely helpful for things like parts A through D. Let's start with part A. Now, part A wants us to find f of 5. Now here we don't have an equation to plug 5 into, but we do have the graph of a function that would correspond to whatever equation it is. And that actually doesn't stop us from answering something like f of 5. Keep in mind what function notation tells us. F of 5 means that we want to consider a specific value of x, namely x equals 5. So when it comes to a graph, f of 5 is related to a point with an ordered pair having the x coordinate as 5. So I'm going to set it up this way. We're going to look for a point on the graph that has an x coordinate of 5, and we're going to try to identify what the y coordinate is. And if we can identify what the y coordinate is for x equals 5, that's going to be our answer. Is there a point on the graph with an x coordinate of 5? And if so, what's the y coordinate? Three. Yep. So this point right here is where we'll get our answer from. Has the x coordinate of 5, and that 3 right there in the context of functions is what f of 5 is equal to. So our answer here is 3. If that's making sense, go ahead and see if you can figure out what the y value is when x equals -2 using the graph of this function. Yep. So this point, -2, 1, helps us with that. The y coordinate of 1 is what f of -2 is. Now for C and D, they actually provide us with specific y values. And let me explain why. Keep in mind that function notation, f of x, replaces the variable y. So to say that f of x is equal to 0 is equivalent to saying that y is equal to 0. So in this instance, we want to look for any points that have a y coordinate of 0. And then whatever the x coordinates are, those are going to be our answers. Okay, are there any points on this graph with a y coordinate of 0? Yeah, actually, how many points have a y coordinate of 0? 3 of them. Yep. We've got 0, 0, 4, 0, and 6, 0. So these are all points in which the y coordinate is equal to 0. In other words, we could say that f of 0 is equal to 0. Actually, yeah, I'll write it this way. So f of 0 is 0. F of 4 is equal to 0. And f of 6 is equal to 0. So these x values are what generate y values of 0. So they're going to serve as our answers. And I'll just write it out in kind of a list format. X equals 0, comma 4, comma 6. Let me have you try this out with f of x being set to a value of 3 instead of a value of 0. Anybody think they have it? So this one, we want to look for a point with a y coordinate of 3. And whatever the x value is that corresponds to it will be our answer. Yep, we actually kind of looked at that point already, didn't we? F of 5 is equal to 3 from this point. So that means that the x value giving us a function value of 3 would be 5. So x equals 5. That all making sense? Okay. Well, now we're going to mix in some inequality notation. It says for what values of x is f of x less than 0? Write your answer using interval notation if necessary, and we'll see why that's included now. But I want to give you some tips here. Number 1, f of x is greater than 0 means that the graph is above the x-axis. The reason for that is because f of x, again, is the variable y, and if we want positive y values, those are only going to happen in quadrants 1 and 2. Okay, so Q1 and Q2, just to add some detail there. My second and final tip here is if we are looking at the notation f of x is less than 0, this would ask us to look at a part of the graph that is below the x-axis. Because this is saying that y values are negative. So specifically, we'd want to look for any parts of the graph that are in quadrants 3 and 4. Now our problem is f of x is less than 0. Is there any part of this graph that is underneath the x-axis? If so, which quadrant would that be in? So keep in mind, our x-axis is the horizontal axis. It looks like there's a piece of this graph under the x-axis that's in quadrant 4. Yep, 4th quadrant. This part of the graph satisfies the inequality f of x is less than 0. Because what would all the y coordinates of these points be? All the y coordinates of this pink part of the graph I just shaded, all the y coordinates of those points would be negative. So how do we represent our answer though? Well, keep in mind it says for what values of x. So once we identify the part of the graph that's relevant to the inequality, our answers are going to come from the corresponding section of the x-axis. And that section of the x-axis that corresponds to f of x is less than 0 is the part that's between x equals 0 and x equals 4. So all of these x values that I shaded on the x-axis satisfy the inequality f of x is less than 0. They have y values that are negative. That's why they ask for interval notation, is because it's all of these numbers between 0 and 4, not just 0, 2, and 4. It's everything in between as well. So the answer would be 0, comma 4. And since there's no bar, we'll use parentheses on both the 0 and 4. Okay, and that looks like an ordered pair, so I'm just going to note that it's interval notation. If you look at part F, for what values of x is f of x greater than or equal to 0? Which parts of the graph do we want to look at this time? Parts that are under the x-axis or parts that are above the x-axis? Parts that are above, yeah. And how many parts of the graph are above the x-axis? Well, we've got a part that's in quadrant 2. When I'm shading in orange, that's definitely above the x-axis. And then we have this part of the graph in quadrant 1. This is definitely above the x-axis as well. So now that we've identified the parts of the graph above the x-axis, we need to shade the corresponding section of the x-axis. I'm going to look at the part in quadrant 2. The x values corresponding to this orange piece that I shaded would go from -4 all the way up to 0. And then the part of the graph in quadrant 1 is using the x values between 4 and 6. And so there are going to be two intervals for this answer. -4, comma 0. Can anybody tell me why I'm using brackets on these numbers? That's because we have a bar this time. All right, so we can include x equals 0. Or I'm sorry, x equals -4 and x equals 0. We're going to union this with bracket 4, comma 6. Does that make sense? Questions, comments, concerns, winning lotto numbers? All right. Melissa, you had the winning lotto numbers? Feel free to send me an email with them, all right? We'll split the earnings. Sound good? I'm just messing around. Awesome. All right, gang. I'm going to actually kick parts G and H off to you folks. All right? Determine the domain and determine the range. Use interval notation for each of these. I'll check in with you in about a minute. All right, any offers on the domain? Let me ask you this. What's the smallest x value being used for this graph? -4. What's the largest x value being used for this graph? The largest x value is 4? I would say 6. All right, here's our starting point, -4, comma 2, and then here's our ending point. So -4 is the smallest, 6 is the largest. Are all the x values between -4 and 6 being used to generate points? Yeah, this graph is fully connected, so don't be confused with just the points that have labelings. If it's fully connected, that means there's more than just those points whose ordered pairs are emphasized. Every point going from -4, 2 to 6, 0 implies that an x value is being used to generate it. So any x value between -4 and 6 is actually part of this graph's construction. So for that reason, interval notation, bracket -4, 6. That would be our domain. What's the smallest y value on the graph? Yep, -2 is our smallest y value. It comes from this point right here. And our largest y value is 3. And all the y values between -2 and 3 are involved in some way, shape, or form in the points on this graph. So any y value from -2 to 3 is being used. So our range should be interval notation as well, -2, 3, bracket on each. Does that make sense? All right. So I've got an exercise for you guys on page 3, where we're provided the graphs of two functions, and it can be a little disifying. That's quite a busy coordinate plane there. But let me try to make it a little easier on the eyes. At least that's my intention here. I'm going to highlight the graph of f of x in yellow and the graph of g of x in pink in honor of SpongeBob and Patrick. Now, let me explain the concept here. So remember when we were reviewing those problems at the beginning of class, I mentioned how some notation would look if you're being asked to add, subtract, multiply, divide two functions. And we're actually seeing an instance of that in parts A through D of this example. But what's a little bit different than what I presented is that there are specific values of x this time. That doesn't change how we rewrite the problem, though. So for example, in part A, we can still rewrite this as f of 6 plus g of 6. And since we have the graphs of f and g instead of the equations, it's going to boil down to adding the y values that correspond to each of these x values. Now, let's maybe work part A together, and then I think that'll probably be enough for you guys to actually take care of B through D. F of 6. Now let's look at the yellow graph. Which point on the yellow graph would correspond to an x value of 6? Would it be 6, 1 or 6, 0? 6, 0. Okay. Now g of 6 is going to be found by looking at 6, 1. And what are we really doing with these points? Well, we're going to replace f of 6 with what it means on the graph. And what it means on the graph is the y-coordinate. So this 0, that's the y-coordinate of this ordered pair. That's what f of 6 is equal to. And then the 1, it's part of the ordered pair 6, 1. That's what g of 6 is equal to. So let's replace these with the y-coordinates to get 0 plus 1. And in honor of Schmidt-Verbenmann-Jensen, who was number 1, that's our final answer. Any questions about that? Go ahead and see if you can figure out B through D. It might help to first rewrite the notation. And then much like we did in part A, you'll want to operate with the y values that correspond to these particular x values. All right, so I'll give you a couple minutes to work on that, and then maybe I'll call on some volunteers, all right? Any offers on the answer to part B? I got -3 as well. Yep. F of 4 is 1. G of 4 is -3. Multiply those together, should get -3. Any offers on part C, which can be rewritten as f of 2 minus g of 2? All right, do I have confirmation on an answer of 1 for part C? All right, thank you. Owen's grinding them out there. Gotta love it, gotta love it. Yeah, go ahead.
I have a silly question. How do I determine when I subtract two y values? Do I use the upper one first or the lower value first?
You use the one that's associated with the first notation.
Oh, okay.
What I mean by, yep.
Okay,
So,
I see. I see.
Yep.
Thank you. Sorry.
Oh, no problem. Great question, though. So we're looking at 2 minus 1 for that, giving us 1. Okay. Any offers on part D? What do you guys think about negative 1/3? So keep in mind that f of 4, we actually have that up here in part B solution. F of 4 is 1, and g of 4 is negative 3. So you can just simply set 1 on top of negative 3, or you could rewrite that as negative 1/3.